Thank you so much, Ben, and welcome everybody. I know that the second half of the Netherlands-Australia football match is going to start, but thank you so much for staying with us. So today's subject is thinking distributed, the Hazelcast way. So let me give some short background of myself. I'm one of the Hazelcast co-founders. I've been Java developer since 2005. Worked in some financials and telcos before joining Hazelcast back in 2009, and then since then I'm with Hazelcast, and right now I'm leading the Hazelcast technical operations, which means giving support to the customers and all basically field engineers and etc. So if you are a customer of ours, I'm super happy to be helping you. Also, please follow me at Fuad on Twitter. I'll be announcing when we will post the slides for the presentation, the codes that I'm using here, and also we are recording the webinar, so that will also be available. I'll announce it there, and some other Hazelcast stuff, of course. So the agenda for today is going to be, to do a very brief Hazelcast partitioning basics. So, in order to be able to utilize Hazelcast very well, especially the distributed nature of it, it's super important to understand the basics of how the partitioning works within Hazelcast. When we say data is distributed, what we mean by that, and etc. So I'll be doing like 5 to 10 minutes of introduction to that, and then I will start with an example. If you have watched my previous webinar, it also used the same shopping cart example, but that was looking into the serialization. In this case, we are not going to be looking into serialization, but we will use the same example to discuss a problem and then provide 8 possible solutions to that. Each of them, of course, has its own advantage and disadvantage. And we'll just talk about those, and gradually we'll actually increase the level of Hazelcast usage as we go through. What I would like to do in this webinar is to make it as much interactive as possible. I haven't done this before, and I don't know how effective this will be, but let's give it a try. So what will be is, I'll provide a solution, and then I'll ask a couple of questions on how we can improve that. And if you can put your answers onto that question box on your GoToMeeting tool, I'll basically look into the answers, and this way, we'll try to be interactive as possible, and I think that will be fun. And at the end, we'll have a Q&A session, so you'll have a chance to ask your questions. It's possible that I'll cover some of those questions during the talk, so just note your questions and ask them at the end. We believe that it is more effective that way. So yeah, let's talk about the data distribution, right? So within Hazelcast, we've got a concept of partition. So it's so the default number is 271. You can think of it as a virtual basket or virtual shard. So what we do is, given any key, we serialize that key, and then we hash that key, and then we mod that hash to the partition count, and we get a unique partition ID, right? So no matter how many nodes you have in the cluster, the partition ID for a given key will be always the same. And all the members in the cluster actually are keeping a partition table, partition lookup table, which is updated frequently whenever there's a change in the cluster topology. So by looking into that partition table, any member can identify where that key belongs to, right? So in a single node, partitions are going to be owned by that single node. And in a one node, of course, there's no meaning for a backup. So what happens is all those partitions are held by this single node. So let's see what happens if we have 2 nodes, right? So when you start the second node, it will join to the Hazelcast cluster. And as you see over here, those 271 partitions are actually going to be equally divided by these 2 nodes. So like for an example, from 1 to 135 are going to be stored in the first node, and the rest are going to be stored in the second node. By the way, this 271 number is just a prime number. We believe that it is a very good number for clusters up to 50 nodes and that hold, like 30, 40 gigs of data. For bigger clusters or for clusters that hold more data, you can definitely set that 271 to a bigger number for a better efficiency. For our use case, it's just okay, and for many use cases, 271 is good. You can change it at the beginning, but you cannot change it once we have the cluster. So if you anticipate to grow beyond 100 nodes, you should set that before. Otherwise, it's just a good number. So that being said, also look into the partition. So over here in this picture, I've noted the red ones as the backups. So as I said in the beginning, the partitions are going to be divided into two. So one node holds the first set, the second node holds the second half of the partition set, and the backups are also going to be vice versa, right? So all the partitions that are that are owned by node 1 are going to be backed up on node 2, and vice versa. So far, it's actually a mirror, right? So it's sort of a replicated scenario where both nodes has all of the data available to them. But it's going to be more, of course, makes sense if you have 4 nodes. In that scenario, again, as you add more nodes, in the background will migrate some of the partitions to the new nodes to make the system equal. Again, as an example in this, so it's actually happening very randomly, so you cannot say which partition is going to end up on which node. But as an example to make life easier, so I put like from 1 to 67, let's assume they're going to be owned by node 1. The second quarter will be owned by node 2, and third and fourth are going to be owned by node 3 and 4 respectively. Also, look into the backups, and as you see, the backups are also distributed. So what we mean by that is all the partitions that are owned by node 1 are actually backed up equally on node 2, 3, and 4. So what that means is, for example, partition 1 is backed up on node 2, 2 is backed up on node 3, 3 is backed up on node 4, and then 4 is backed up on node 2 again. So this way, actually, all those partitions are distributed on the backups as well. So if node 1 goes down, we know that all those partitions are equally owned by node 2, 3, and 4, and they will just declare it as primary, and then in the background, Hazelcast will do one more step of the backup to make the system high available again. But so far, what we need to know, I mean, we can talk a lot about how that happens, but I don't want to focus onto that. So far, what we need to know is, the backups are equally distributed, the partitions are equally distributed. So in terms of Hazelcast, it only knows the concept of partition, and any key, given any key, we can calculate that, we can hash that, and we can find which node actually owning that partition. So this way, given a key, given an operation, we can think how that's actually going to be resolved, right? So let's do a scenario. For example, let's assume that we're going to map of airports for a simplicity, and the key is the a small 3-letter keyword for the airport, and the value is the long description of it. And so when we do a map that puts SFO and there's a value San Francisco International Airport, I didn't calculate that, but let's assume that when you serialize SFO and then hash it and then mod with 271, let's just assume that it gives you the number 200. Okay, for the simplicity. Honestly, I didn't calculate that. So given that, so when you do this map.put operation, so what happens is any node can initiate this operation, right? It could be a client that initiating that, or one of those nodes that is initiating it. It doesn't matter, but the operation first will come to the owner of it, right? So, and in our schema, we assume that partition 200 is owned by node 3. So in that case, first that put up come to node 3, and then node 3 will actually perform it. So it will perform the put operation locally. It will for that key, so it will perform it, and then it will look who is the backup in that partition table, and it will realize that, let's assume again for this case that the node 2 is the backup for that partition 200. So it will send the backup, it will send the same operation to the backup, and it will notify the sender. So see the arrow 3, it will also notify the sender, will say that I did the operation, and you should also receive a response from node 2 as a backup. Okay, so the initiator of the request knows that the primary operation is done, and it will wait until the backup is also done. So this is how the put operation is happened, and as you see, it will only return after the fourth part of the this operation is done, which means that the backup will return a response to the initiator of the call, and then it will be done. So we will know that the operation is successful both in primary and then backup, and then we will return the call. So this way, actually, the backups are synchronous. So when you do a put, you know that the data is changed both in the primary and the backup, and then you return it. We'll also have an option to make the backup asynchronous, and then in that case, the fourth leg of the operation will be actually asynchronous, and the initiator will not wait for that. So it will basically wait for it in the background, but it will not block the call until the fourth leg happens. So that's how basically the data is distributed. A put operation is performed. All the operations related to the key basically happens in the same way, right? When you do a lock, it exactly happens in the same way. It first goes to the primary, locks the keys there, then goes to the backup, locks it there, and then returns. Or if you do a replace method or remove method or an evict method, the arrows are going to be flowing in a very similar way. And let's do a read operation. Of course, read is a relatively simpler operation. In that case, again, we calculate what the key is, which partition, in which partition the key is, find the member, send it to that member, and then that member is going to be returning the value to us. Of course, again, do not forget that the system is very distributed. So when we do that, in many times we're going to a remote machine. So the data is always serialized and deserialized. So in that case, the key is going to be serialized. It will send to the node 3. Node 3 will look into the binary representation of that. Will find the value. By default, the values are stored in serialized format, and then it will send that binary information back to the caller, and that on the caller side, be it client or be it another member in the same cluster, it will get that byte array and then deserialize it and return as an object to the call. So that's basically how we do the hashing, how we do all the operations, and etc. I hope this is understood. And given this background information, now let's talk about our use cases. Okay, so I created, again, let's assume that we are doing an Amazon-like website where we've got items that we are selling, we've got a shopping cart, shopping items, people are adding those shopping items into the shopping cart and then checking out. To make it more dynamic and more like a challenging environment, let's assume that our Amazon-like e-commerce website is at some period of time just does some crazy discount, and everyone is doing a lot of transactions. So we need to have very high available, very scalable system that can deal with all those concurrence issues and etc. Okay, so let's just assume that this is our problem and this is our system that we want to build. So what I first build is my domain object. So a shopping cart item is very simple. It has 5 properties: cost, quantity, item name, the Boolean value being in stock or not, and the URL for the item. And then Also, again, note that I'm not trying to look into the serialization part of it. So my items are just implementing serializable. I haven't done any improvement for that. And also, I will be doing some benchmark-like number. I will be showing some benchmark numbers. Again, these are not a true benchmark. My idea here is not to do a true benchmark and show you the results. And we are here just trying to discuss the different solutions to a given problem. And I only run these example on my laptop in a 4-node cluster. Of course, it is not the ideal way to run that such a thing. It has some extra cost of serialization or object creation within it, so it's not perfect benchmark. I admit that. But the idea is to look into the numbers in a relative aspect to see relatively how the numbers how different use cases perform within each other. I mean, you are free to go and run this in a more serious environment. I actually do plan to run that on our stabilizer environment with a true micro benchmarking and etc. to have a true numbers results as part of our Hazelcast performance testing. But so far, again, I warn you that these the numbers that I will be showing to you are retrieved from my laptop, so they are not perfect. They are not ideal, but relatively, they are good for our use case. They will give approximately, they will help us to analyze different use cases approximately, and usually they will make sense once you understand how the system is working behind the scenes. So this is my shopping cart item. And also I've got this shopping cart, which is, contains a list of items and also has a total cost. Whenever we add an item to this list, we also update the cost, and we do the same when we remove it. So it's a very simple, again, implement serializable, no improvement there. And, if you saw my previous webinar, if you do actually, use Hazelcast identified data serializable or even cryo for that, we will definitely achieve very high performance gains there, but I haven't done it just to make it simple. So now here's our simulation. Again, this is just a simulation of the system, right? We are doing a POC. We want to see, how our system, how our implementation is going to perform. So for the sake of this simulation, here's what I do, right? I'm creating some random key. I've got I believe 10,000 key range. And then given that key, what I do is I'm trying to access a map, an order map, and I will get that shopping cart from that order map. So I've got so the system has a limitation which says that your shopping cart cannot exceed $1,000 amount. So if the item is less than 1,000, I am adding a random item into that, simulating adding an item into my shopping cart. More than 1,000, I'm removing something from it. So that's just as simple, and putting the shopping cart back. Again, this is not ideal. This may not be the actual use case, but for this use case, I just implemented that. And if you run it, so let me show you how I am actually running that. It might be a little bit of an ugly code here. So I've got this Amazon example. So what I've got here is I've got here a performance tester, which, let me make this bigger for you guys, which it's solution agnostic, sort of. I'm creating different runnables which represent different implementations for the solution. And what this class does is it actually executes. I've got, let's see how many threads we've got. Yeah, we'll see how many threads I'm initiating. I believe that's 10 or 20. So I'm creating some number of threads, and those threads, executing all these simulation implementations. So what they do is, while the system is running, they actually counting the system time. They are, doing some stats here. I'm using the HDR histogram to see what's the latency and what's the throughput of the system given those operations. So it's a simple performance tester, and as an input, as you see over here, so this is basically the implementation that I just showed to you. Get a key randomly, add it to a shopping cart, get the shopping cart first, add the if the cart is null, initiate that, and then if the total is less than 1,000, just create an item and add it into the cart. And if it is more than 1,000, remove it from the cart and put it back, right? So, and then I'm basically running this. So let's just run to see how the number look like. So I've got different solutions here. So when I run this, let's do that. So it is going to start 4 Hazelcast instances within the same JVM. And of course, right now, my machine is way more slower than I ran before because of the recording happening, because of the GoToWebinar. So it uses a lot of CPU in the background. That's why the numbers that we will be seeing here are not going to match the numbers that I presentation. So we're not going to run all these scenarios on my laptop, but I just want to give you an idea how that is working. Yeah, so my 4-node starts. I'm going to have 10 threads. Let me see actually how many threads I've got. Yeah, I've got 10 threads here. Yeah, so here I'm just calculating all the operations. It puts a nice histogram showing the percentiles. So for example, the 50 percentile have, I believe these are microseconds, so it's like 14 microsecond latency. Or so yeah, so this is my throughput and etc. So this is basically how I am, calculating it, right? So let's get back to the presentation. So yeah, so I just run this, and the number is, I've got 5,000, almost 6,000 operations per second, and the mean latency is 2.4 millisecond for this operation, which is basically has how many? Let's say 2 actually distributed operations within it, right? First it does a get, and then it does a put. So far so good, right? But something is actually wrong here. Now this is where I want you guys to be interactive a little bit. Can you guys tell what's actually wrong with this implementation? Let's see if this interaction is going to work or not. So please type your answers to the question mark, and I'll be seeing them as an answer here. So what is wrong with this implementation? Something is actually not correct. Yeah, thank you, Peter. You are the first, Peter Potts. Locke, Greg. Yeah, great guys. So definitely this is not atomic, right? Yes, it does make 2 network hops, but the problem here is that, yes, there's a race condition. Marsh mentioned that. So thank you, guys. So it works, the interaction works. So yeah, it's not atomic, right? So we shouldn't be doing that. We've got actually a customer here in Bay Area which does a similar stuff. It's not a shopping cart, but they are synchronizing the content of from your phones or iPads, saving them in the cloud and making them, ready for everyone. And that scenario where you could have been starting the synchronization at the same time, both from your iPhone and iPad, and to make sure that we are not actually overriding an item, and to prevent the race condition, they are actually using a locking. And actually, one of the use cases that we're going to be discussing here But yeah, so what we need is actually locking, right? So that's not good. So we need to locking to make the system, um, yeah, to make the system uh, atomic, right? To make the operation atomic. So what we do now, we first lock the key, and then we do all the operations, and at the end we unlock it, right? So in the finally, we unlock it. So far so good, and I did run the numbers as well with this system, and now the performance actually dropped, as you see, from 5700s to 2700s, right? And the average increased from 2.4 millisecond to 3.7 milliseconds. So it definitely shows some change. Now, again, if we see what we are doing here, we are first doing a lock, and then we are doing a get, and then we are doing a put, and then we are doing an unlock. And as you see, all these four operations are actually distributed operations, and lock, put, and unlock are actually an update operation. So they are performed both on the primary and on the backup nodes. So it's actually pretty heavy weight. So if you count the number of distributed operations here, that's actually 2 times 3 plus 1 for the get, which is just one distributed operation. So there's actually 7 distributed operations, and one can say that this is very heavy and costly. So so how we can actually improve that? Do you guys can you guys think any other solution where we could improve this? Again, you can type your answers into the question box on your GoToWebinar. Yeah, so there's a question actually, what if the record is already locked? So the lock will just wait. So it's a pessimistic locking. So if someone is else already doing an update here, so the other thread will wait until the other one is done. So that's definitely a heavy operation. So there are definitely like some, yeah, I definitely see some nice solution suggestions here. We're going to be talking about all of those. But for now, I'm actually, let me see, I'm looking for the one that will be the next one. So lock should be made at individual operation level. Yeah, okay. Use the concurrent map. That's correct answer. Yeah, pretty good answers here. So let's go one by one, right? So actually, one thing that we can improve, remember, I said that there's actually 2 operations. So we do the lock first, and then we do the get. So there's actually an operation in the transaction API which says get for update, right? So the get for update is gets the value and also locks it. So we basically combine both read and write into same operation. So let's discuss this, right, as an option. So it's actually pretty similar to the locking. So in the database world, we have this transaction concept. So we have the same within Hazelcast. So we've got the XA transaction and the yeah, there you go, the Peter Potts, put that lock and get, put an unlock. So yeah, exactly, we are doing the same thing here. So we are starting transaction. We are doing a get for update, right? So which basically reads the value and also locks it for us. And then we do exactly the same stuff that we did before. We put it back and we commit. So this put actually does not happen when we do that. It will only happen when we commit the transaction, and it will automatically do the unlock itself together with the put. So it's pretty optimized. But it's an XA transaction. So let's use the XA transaction first. As you see here in the transaction options, I've selected it to be 2-phase. However, let me explain actually one thing here. When we say 2-phase within Hazelcast, so our XA transaction is phase, and plus it also saves the state of the transaction on multiple JVMs to prevent the partial commits. So our local transaction is actually also 2-phase. It also has in the first phase it does the lock, in the second phase it does the commit. So it is still 2-phase. If you look into some other product in the market, which has XA and local transaction support, their XA transaction is actually equivalent to our local transaction, because we also do the same locking and then commit in our local transaction. However, our XA transaction has an extra step of saving the transaction logs in a multiple JVMs to prevent partial commit. So when we do the commit transaction, it actually first does the prepare, which saves the state on multiple JVMs, and once it is saved and secured, and then it does the commit. And while the commit is happening, if this JVM crashes, so if the guy who is doing the transaction, if that crashes in between before the commit transaction returns, we've got the state on other JVMs and they can actually finish it. So it prevents the partial commit. So it's actually very heavy implementation, and when we next slide, and when we run this, actually we see it's actually even worse than the lock in terms of the throughput. But there can be scenarios where you need that, and where you can use XA transaction. But the XA transactions are really good if you have multiple resources that you update, right? That's where two-phase commit is very good for. So you have multiple resources, multiple transaction resources, and you are using two-phase commit in between them to do the distributed transaction. But in our case, we actually have just one map, right? We do not actually need the XA transaction, and we can be very, very happy with local transaction as well, right? So so yeah, my question here is that we didn't improve. Why? I actually gave the answer why we didn't improve, because of the heaviness of the XA transaction itself. But yeah, let's discuss the local transaction. So so the next one, the fourth implementation, I've chosen here is the local transaction. So so in the local transaction, of course, it's exactly the same thing. We just marked it as a local, which means that we're going to have just two-phase, not three-phase, not prepare phase. So and if we run this, and the numbers are going to be actually, not so bad compared to our lock example, right? If we go back, so let me look. How was that, right? So our lock example was actually our the first example. Our lock was pretty bad, and now with our local transaction scenario, where we actually improved the lock, instead of the lock and then read, we are doing a get for update, and when we commit, it also does update and unlock. So this way, we actually reduce the number of distributed operations. So we are atomic, just like the lock. So instead of lock, we are using local transaction, and we are pretty good. Not maybe as good as without. It's actually very close to doing it without lock at all, right? So it's pretty good. So yeah. So now the question is, can we actually do it without a transaction, right? So that will be my question to you guys. So what else could we use? I know actually some of you guys already answered this question in my previous time, but yeah, go ahead and suggest other options that we can use. And you may want to also put a comment saying why another alternative would be better than this one. Yeah, how about replace? Rahul said that. Using a sync queue. Wow, that's interesting. Yeah, that might be another alternative. You're just putting the operation to the queue, and there's maybe some threads that are consuming that. Well, then the queue is also going to be a sort of a bottleneck. I'm not sure whether that will perform any better or not. Yeah, send an update function. Yeah, timestamp ordering. Could be. But okay, let me. I mean, all those are actually, to some extent valid, and we may need to try them. I've definitely tried. We're going to be talking some of these here. So So the transactions that we are using here is actually yeah, I'm looking to the answers, guys. Sorry. Yeah, so the local transaction, so Eric asked how the local transaction works. So the local transactions, again, it first does the lock on multiple JVMs. So given all of your resources, it does the lock for them. And then when you start to, and when you do an put, it is stored in this local JVM. It's not processed yet. And when you do the commit transaction, then it is actually processed, right? So, so it's, again, very atomic because of the locks. But since the transaction API is optimized, it has this get for update methods, and on the commit transaction, it does with put. So it's very optimized, and it performs much better than doing lock for your own. But in theory, it's exactly similar to locking a key and then reading it, putting it back, and then unlocking that. So it's very similar to that. So, but as you see, it will lock the key, right? It's actually an implementation of a pessimistic transaction. So when we are locking that key, if there's another thread who wants also to do a similar operation, it will be actually blocked until this transaction is committed, right? Because it will also try to do a get for update, but it will not be able to do that because there's another thread who already locked it. So it's sort of a blocking operation in a sense. It's really good if you've got a lot of contention on the same key. So if the same key, let's say you've got only 10 keys and you've got like hundreds of threads that are doing that, then having a pessimistic locking is really good because you know that there's a lot of contention on that, and doing a lock will guarantee that a thread getting the lock will perform it and then will release that. However, if you know that there is not that many contention on a given key, then instead of doing a pessimistic locking, we could actually do an optimistic locking implementation, right? Some of you guys already suggested that, like CAS operation. So that's a compare and swap. It's actually pretty good to use instead of locking. So remember the customer I mentioned that is using this synchronization application. They actually first implemented it with locking, and then when we visited them, we actually suggested them to use compare and swap, because the only contention that they could have is the same guy, synchronizing his contacts both from iPhone and iPad, right? So most of the time, when you do that operation, there won't be any lock happening. So why to do lock first, get first, and stuff like that. So instead, we can use actually those concurrent map operations, the CAS operation that concurrent map provides. And given that Hazelcast implements concurrent map, we also provide those. So so basically, the implementation now is going to be, instead of doing a lock or doing a transaction, so we actually assume that nothing is going to happen. No one is going to be doing an operation at the same time. So we just freely go read the data. We update our data, and instead of doing a put, we are actually calling put if absent, right? So if the order was null. So first, when we read that back, if we see that order was null, so we basically keep that state. If the order was null, we are doing a put if absent, which means that I am I think that I'm the first guy who is doing the first put, so I'm calling put if absent. If the order was not null, which means that okay, now order wasn't null, so then I'm assuming that I'm the only guy who is updating this order, so I'm calling the replace method. Now see that the replace method takes both the old card and the new card. So it says that okay, here's the key. Here's the state that I assume you are in. So, and here's the state that I want you to be. If you are still in this old state, please do my update. Otherwise, let me know with a Boolean if you are done or not. So now the replace method and put if absent method both returns a Boolean. and that Boolean will tell me whether I was successful in updating it or not. If I am successful, it means that I was the only one. I actually didn't have to worry about the locking the key. So I'm pretty good. Again, if there is no that much contention, it means that pretty much I will be the only one. Maybe once in a while, there will be some other guy, trying to do an update on the same. In that case, my method will actually return false, right? So remember, just note that now, in order to recover from that state, what we're doing here is that we're actually putting all this code into a while loop. So it says that while I'm done, try to read it and update it. If you are not successful, try that again, right? I will read that again, and I will add that again, and then I will replace that again, right? So it's in a while loop. Again, if you have a lot of contention, it's possible that many times you're going to be receiving false from this CAS operation. So you will do a lot of so your while loop will basically iterate a lot, which means that you are going to be actually doing way more distributed operation than doing a lot. So again, if you've got a lot of contention, doing pessimistic transaction is better. But if you do not have a lot of contention, then doing a compare and swap within a while loop is much better, because most of the time the while loop will just iterate on the once. Only once in a while it will do more than once. And in this case, we are just reading, which is one distributed operation, and we are updating it, which is two distributed operation. So with just three distributed operation, we are basically handling it. And again, this is atomic. And when we run this, actually, as you see, the performance is somewhere in 6,000s, and it's actually pretty good, right? Yeah. So. Yeah, now the question is, what other options do we have, right? What else we could do? And you guys already answered this, so I'm not gonna wait for your answers. All of these are really beautiful, but remember, even now we did like three distributed operations, right? So if now the idea within Hazelcast, within these in-memory data grids, most of sending your execution actually to the code, right? This way you can make your code local to the data and actually reduce those distributed operation calls. So of course the best tool, not the best, I would say, an option to do that within Hazelcast is executor service, right? So what you do here is you just create an executor service, and you create a runnable or callable, and in this case I call that put with lock. So that's a runnable. I'm not really interested in the value. I don't have a value to return back, so that's why it's not a callable. So what that operation, and if you look into that, I've actually just copied the lock example here. And the reason actually that I didn't copy the compare and swap is I just wanted to show the difference, because compare and swap already was pretty optimized compared to the very first lock example, and to show the the difference. And actually I did try that with executor service, and it didn't improve that much, because again, the CAS example, the CAS implementation already was pretty much optimized. But assume when you do a lot of distributed operations, more complex scenario, and maybe you need to do that in a pessimistic way, and transaction just doesn't work, so you have to do it in a lock way. So just assume the worst, right? And in those cases, if you just move exactly the same code, to the node instead of doing it from remotely, I just wanted to show the difference that way, right? My example doesn't give me much improvement here with moving compare and swap to the operation. But a more complex example, if you do that, if you just copy paste almost exactly the same thing and send it to the data, and if you run it now, instead of 2700, now we get like 3700 throughput. So the latency is a little bit higher, but the throughput is actually much better. So yeah, so by doing that, you can definitely improve your throughput as well. The reason the late, yeah, okay. Now the question is, can we move it any closer? Yeah, feel free to type your answers to the question box. Yeah, there are some suggestions coming in. Kevin said enter processor. Yeah, exactly. That's the answer that I was looking for. We can move it even further with enter processor. I will explain why is that important. There are some other answers as well, like using partition aware. Well, I believe we are already using it. Let me see. Um, uh, well, partition aware is actually going to be exactly the same as um, instead of saying to the executor service that execute this operation in this key, if you have that operation implementing partition aware, it will be the same thing. So it's another way of saying where to execute the data. Another answer saying in near cache, well, near cache may help in the reads, but actually in this particular example, we have the same number of read and update, so near cache will not actually help us in this. Map reduce the data. Yeah, I haven't actually tried for this scenario map reduce because it's not actually about doing some aggregation and etc. It's rather doing some updates. I don't think that map reduce is going to help here. Honestly, I haven't tried. Yeah, maybe we can try that and see if that helps. But yeah, thank you, Kevin. You already mentioned that it's enter processor. So definitely another way to do it would be doing it with enter processor. Now, the difference between enter processor and executor service is actually pretty huge, because enter processors are more native to the map. And when you execute them, they are actually executed on the main service thread for that partition that basically normally does all those puts and gets. So when you send an operation with an enter processor, it's actually almost the same as you are sending an operation, right? Being it a get or a put. But when you do it with executor service will just co-locate the same operation to the node and will use its own executor service threads and submit that. And when you do a put or get, it will basically, for example, when you do an update, it will update the local one. It will be local to itself, so it will be fast. But the backup will need to copy the entire state to the backup object. But with enter processor, you can actually do delta updates, right? Now, let's look into the implementation, and I'll tell you how we are doing the delta updates. So the implementation says that, so now we've got an update enter processor. So let's look into the first part. Again, instead of doing map.put get log, I'm just doing map.execute on key, and here's the update enter processor. That's it, right? I'm not worried about anything else. And then in the body of this, I'm doing the same thing, right? Now this is more native, so it operates on the entry, but the given the key. So I will read the I will do entry.get value. I will read it. If it is null, I will create the shopping cart. If it is less than 1,000, I will add one. If it is more, I will remove it. And so you need to set the value back to the entry. I'm not interested in that value, so I'm just returning null here. So this is how I'm doing the process, right? Adding one item into the shopping cart. So now on the backup, again over here, I'm actually creating the item, on the remote node. So the real example would be actually, you created the item, you put that in the entry processor itself, and then you send the item that needs to be added there. So that's basically how it actually should be. But anyways, now look into the backup though. The backup, it's actually sent the exact same operation to the backup node. So instead of updating the backup object, we are actually sending the operation to the backup as well, and we say that okay, now just apply the same operation there. It's as if you are saying just apply this delta to the backup. So yeah, so this way we are basically saving a lot. And when I run this, I've got 7,000. It's definitely much better. But actually, there is more improvement that you could do, which is one more thing that you can do with interprocessor is actually setting the map, so storing the data in the object format. So by default, when you do in operations like get, put, storing the object in serialized format, like meaning binary format, is actually very good because most of the time remote machines are going to be reading it. So storing that in ready state is really good for you. But if you've got a map where you are doing entry processor on it, storing the objects for that map in the object format is actually much better, because when you do entry get value, entry set value, you will not have to serialize and deserialize on that node, right? So you'll just send the entry processor to the node, and the object is already waiting for you there. You'll just apply the logic, and you'll do the same on the backup. So basically, the entry processor itself will operate much faster. And when I did change it to the object format and rerun that again, so I get much better values. The latency is almost down to 1.1, 1.2 millisecond from 2.4. Remember that. So from 2 distributed operation, I'm basically just doing 1 distributed operation, and that's it, right? So it is much better. So in terms of operation. So yeah, so we started with a non-atomic way. We did locks, we did XA transactions. Then we did CAS operation, then we did executor service to bring the processing to the data, and then we even made it more native to Hazelcast. We used interprocessors there. We used the fact that we can store the data in the object, and we used the fact that we can do the updates in the delta format. So of course, if you are doing, for example, if your interprocessor is not actually doing any update, but rather doing some sort of aggregation, then your backup interprocessor can even be null, right? You don't even need to send that to the backup. So it's actually very optimized in that sense. And of course, if you apply the serialization improvements, you can even improve further in that. So yeah, one last thing that we could do here is, instead of using a map, we could use a multi-map and use a different domain object. So instead of having a shopping cart as a map, we could have a maybe atomic number that will be keeping the total for a given ID, and also we could use a multi-map that could store all the orders for a given ID again. So instead of having one map, we could replace that shopping cart object with a multi-map and atomic reference, and basically use that. That would be a different scenario. I haven't done that, but that's also an option. So instead of using a map, because multi-map has very nice methods like add and remove from the collection. So instead of you reading the map, updating the list within that map and then putting it back, multi-map can just add or remove an item from its list in an atomic way already. So that would be another format. So definitely, I'm now we are 5 minutes left for the end of this session. So feel free to ask your questions. In the meantime, let me do a shameless announcement here. We are definitely a growing organization here. We are hiring. So our immediate need is some solution architects here in United States. So if you guys looking for a job, familiar with Hazelcast already, please feel free to send your resume. So yeah, go ahead and ask your questions. How we solve the thundering herd issue if calls are blocked? The above question is on the put request. I don't know what you mean by thundering herd issue. Yeah, if you can re-ask that again, that would be great. Yeah, definitely the slides are going to be available later. We will post them on Hazelcast website. We will post the webinar. I will upload GitHub, and they will be available probably in 1 or 2 weeks on the website, and I'll be tweeting that on Twitter as well. Does each partition have block size limit? No, there's no block size limit. Yeah, you can store terabytes of data within the partitions. Yeah, as you add more data, the partition size will be basically growing. How is memory handled when you create the maps? When you would create the maps, so every node is going to be having a small map created for them. So having thousands of different maps may not be very ideal because that will be relatively costly. Each map has a couple of megabytes of overhead, but yeah, it's distributed among the members. I don't know if that's enough for the answer. Yeah. The question is, could you clarify why executor service slower than interprocessor? So executor service, so on the executor service, you do, so first of all, remember on the executor service, we still had to do lock, read, put, and unlock, right? So 4 different operations. So yes, all of those are local, but remember the updates still have a backup that definitely are going to be on a remote machine, right? And if your object is actually pretty big, even if you did a local put on the local machine, still the backup needs to to do the backup, you need to copy that object to the backup node and do that there, right? But with interprocessor, actually, given the fact that interprocessor is executing that logic on the service thread that is responsible from that partition, it also automatically guarantees the atomicity. So it guarantees that while that process is being executed, there cannot be, by nature of by the design of Hazelcast, there cannot be any other thread that is also executing that same thing, right? So you actually do not need even to do any locking or transaction when you are doing that with interprocessor. So interprocessor saves you from locking or from worrying about atomicity, and plus interprocessor saves you from copying the object to the backup as is. Instead, it just applies the delta. So I hope, Eric, that's clear. Does Hazelcast uses JVM heap, or can we redirect to disk space? So by default, Hazelcast always uses the JVM heap. We've got Hazelcast Enterprise that can also store the data outside of the heap, but as of now, we do not have an overflow to the disk. You can have a map store, and you can plug a map store implementation, and we can overflow to the database, provided your implementation, but that's not the built-in overflow to the disk, and right now we. Yeah, so thundering herd, when multiple threads are trying to put the object concurrently, we are not handling it properly, then same object will be inserted multiple times. Same object still can be oh, I see. Well, we definitely using the transactions or locks. So yeah, definitely that will not be happening if you've got transactional lock. Yeah. Yeah, Hazelcast. So the question is, how large bytes may objects be stored in Hazelcast? We do not have any limit. You can store, as big as you want. But of course, it's a cache. Yeah, we've got users, of course, storing kilobytes, megabytes of data. If you've got, an object that is, way bigger than, I would say, 10 megabyte, then probably, we should think about what you are trying to do in terms of the solution. But theoretically, there's no limit. can we initialize the map with initial memory size and then increase incrementally? A good question. So what we can do is, if you give a size to the map, Hazelcast will automatically evict. If we exceed that size, what can you do is you can give a size in terms of a node. So as you add more nodes, automatically the size will be increased. But your JVM process, right? Let's say if you start with 4 GB of heap, so you should know, what is your limit in terms of the map size, and you should set that properly. And later on, you cannot actually change map size on that machine. We have a dynamic way of changing the configuration through Management Center, and we are planning that to have in our clustered API for the Hazelcast Enterprise. But for now, in the Hazelcast itself, we don't have that capability. How the load balancing works for Hazelcast. So by default, again, given that we serialize the key, we hash the key, we mod the partition count to the partition count. So normally, while your keys are your, some sort of IDs or some objects, they usually tend to, very equally balance automatically. But if we are talking about like executor service and etc., if we are not doing executor service on the key, then it's just pretty round robin. Yeah, but in terms of data distribution itself, it's basically the hashing algorithm. Usually works pretty well. You can easily try with just creating like thousands of 10,000s of entries, storing it 2-3 nodes, and using the management center to visualize how the data is distributed among them. And most of the time it's pretty equal with 1-2% differences. Yeah, so the question is, can we push the config file to every cluster if we add any new node or add any new map or include security? Yeah, absolutely. So, I mean, you don't actually, so the new node coming, it doesn't actually need, so it's just okay to have the old configuration. All it needs is to have, on its configuration, it needs to have an IP of one of the existing running members. So yeah, I mean, normally it's not a challenge, but if the question is, can you update the config after you've added a new member or etc., you cannot. What if Hazelcast crashes? So Hazelcast can be both embedded or you can have a client and server scenario. If Hazelcast crashes, if one node crashes, we recover automatically. All the others are going to be running fine, and the data will be recovered. So if you're on a client side and connecting to the members, so if one of the members crashed, the client will automatically connect to the others. If the entire if everything is crashed, then client does have some capability to reconnect when the cluster comes back, or you can just reconnect itself. But if all the Hazelcast crashes, we are basically starting from scratch. Can I have one transaction in 2 threads? No, you cannot. No, you cannot. A lock is associated with a thread in a member, so you cannot have 2 threads basically sharing the same lock. So the question is, which memory is used by Hazelcast, allocated to JVM or available on host? So Hazelcast, mean open source Hazelcast, it runs on the JVM, so it is going to use the JVM heap. If you want that to be separate from your application, some people create a different JVM process for Hazelcast, even in the same box, and use Hazelcast client from its application to connect that to separate those JVMs. But our enterprise Hazelcast provides the ability to store the data off the heap, which means it's outside of the JVM and it is on the memory of the host. can you cover how backups work when operating on an entry via an entry processor? So yeah, sure. So let's get this one. So when you submit an entry processor, so it's first submitted to the primary, and this is the code that will be executed on the primary, right? So and then it after this is done, it calls this method, get backup processor. So you can say return null, which means that I'm not going to do any operation on the backup. So you can do that if you are doing a read. So if your entry processor is actually doing some read operation, right? It's not updating anything. But if you are updating that, over here, notice that I'm just returning a new implementation of itself, right? New update entry processor. Oops, sorry, I made him. Let me see. No, sorry. So it expects you to create an entry backup processor. So I'm creating a new entry backup processor, but its process backup method, this update entry processor's process method. So literally, I'm sending the same code to the backup as well. So normally, when you do a put, the operation is done on the primary, and then the same object is copied to the backup, right? So it's more of a just copy. You've got the entire state of the object, just replace it with the new state, right? But the interprocessor lets you to do an operation on that entry and change it that way, right? So if we send the same operation to the backup, we'll basically be doing the delta update on the backup instead of changing it on the primary and copying that object to the backup. So we are basically sending the operation to the backup. I hope that's more clear, Kevin. What determines whether the map values are stored in serialized form or object form? It's actually a one line of change over here. Let me see where I've got it. Yeah, so given your config, I want to set in memory format to be the object. So the default is binary object, and off here it's only enabled if you've got enterprise. Yeah, so it could be binary, or so this is the default to do the binary, or you can change it to be the in memory. What will be impact on garbage collection if there are frequently read-write of object? Yeah, definitely there will be some impact on garbage collection. Even if you do just a read, given that you've got the object in serialized format, we in the background copy that and then send it through the wire. So definitely, there will be a lot of garbage creating. There are certain ways to improve that. Allocating more memory JVM heap than you are actually using it helps a lot. So definitely do not use your JVM in its limits. Some general GC tuning stuff can be applied here, but of course Hazelcast operates differently from any Java application because it does store some data. Java assumes that an application is not going to be storing a lot of data in memory. The data will be just created and garbage, soon, which is not the case for Hazelcast, and that's one of the reasons we have, Hazelcast Enterprise, which is able to store, the data outside of the JVM. So you've got a small Java, and most of the garbage is not happening there. A small Java heap. So yeah. Is it a good idea to load terabyte of data doing bootstrap? Given first node is only 5 to 10 gigabyte, how much time it will take to bootstrap? Yeah, definitely loading terabytes of data can make some time. So I'm assuming that you are saying that one JVM, one node can hold 5 to 10 gig, then you're going to need, lots of them. So yeah, of course, loading the data upfront is, I'm not sure if I understand your question correctly, but yeah, loading the data upfront is always wise, and we've got the map loader for that, so you just plug that in, and when Hazelcast starts, it will basically do loading in a distributed way from all the JVMs. So guys, I see that you've got a lot more questions here. So sorry so that I cannot cover all of them. We are 10 minutes over our scheduled time. Thank you so much for joining us. Again, we will upload all the slides and presentations up front. If you think that your question, is very, very please do send it privately to me, fuad@hazelcast.com, and I'll try to get back to you with the answer. So sorry for stopping now. Again, thank you so much for being with us. Have a nice day or evening, given where you are in the planet. Thank you, guys.